We're going to give everyone just another minute or so to get connected to the audio and get everything set up. So we'll be getting started in just 1 minute. Thank you. Hello, and thank you for joining us today. 7 tips for calibrating pressure gauges and transmitters. My name is Tim Francis. I'm the product manager for our pressure and flow calibration products. I'm in the calibration business for a little over 14 years, first at Ruska Instruments and joining Fluke after the acquisition of Ruska in 2010. A copy of this presentation recording will be sent out after the presentation later this week. If you have any questions during the course of the presentation, feel free to send them through the chat or Q&A tools. These questions will be answered at the presentation as time allows. We appreciate your time and your interest in improving the overall knowledge base of the metrology world. Further ado, let's begin and start talking about 7 tips for calibrating pressure gauges and transmitters. So what exactly are those 7 tips? We'll deal specifically with gauges, and some deal specifically with transmitters, and some really are appropriate for also pressure calibrations. We'll talk about how you need to pick the right media, gas, oil, water, and so forth. The importance and how to stabilize the pressure and make sure that the right resolution is being displayed. Preventing contamination. Not healthier, but that our gauges need to be exercised. Dealing with the limited resolution of a dial gauge and how to maximize that resolution. Considering the uncertainty of the electrical measurement when calibrating pressure transmitters, and we'll talk about automating the data collection and the benefits of doing so. About picking the right media. Listen, the pressure is a hydrostatic pressure. That is, it is a fluid, either a gas or a liquid. The media types have different advantages or disadvantages depending upon the application. Let's first at a gas media. This can sometimes be something like a compressed atmosphere, like with a hand pump, where you're compressing the atmospheric pressure, you're drawing in air and compressing it to generate a higher pressure. Nitrogen or similar inert gases, especially those that are available as in a gas cylinder, that could be distilled from a resource. Useful for lower pressures, especially cutoff points are somewhat arbitrary. Say less than 600 psi. Cutoff is given there because that's about the pressure that can be generated by hand with different design pumps very easily. So pressures, you have more capabilities because you have the ability to compress the gas to get to the pressures required. It's often used for high pressures, that pressures greater than say 3,000 psi, due to a number of reasons, but especially for additional safety concerns. With compressed gas, there is a lot of energy stored in that gas. If treated properly, that energy can be dissipated very quickly, causing an unsafe event. So we'll use liquids or liquid media for high pressures due to this concern. It is possible to use gas as a media up to pressures as high as 15,000 psi when required, especially for situations where cleanliness is a concern. That if you're trying to calibrate something that cannot be contaminated with hydrocarbons, so perhaps maybe an oxygen clean device, then calibrate with that gas media. Used for pressures, and is oftentimes used for pressures between, say, 600 psi and 3,000 psi. 3 is also a pretty good cutoff because that's about as nitrogen gas cylinders are available, where they'll provide gas to continue to do the calibrations. Gas cylinders, depending upon the region of the world you're in, can be available as high as, say, 6,000 psi, and those work well when regulated down for 3,000 psi calibration. Well, the key things is it's less likely to cause contamination and very easy to work with at the lower pressures. Is a liquid media. This is oil or water, but not preferred for low pressures. You will see it done, but there are challenges when doing so. Cause additional errors due to head height. Oil, water, especially oil, can residue on gauges and cause contamination in the field. So oftentimes we will calibrate using those low pressures whenever possible, and reserve a liquid media for situations where we have to have liquid as our medium. The high pressures, so it's commonly used for higher pressures, especially greater than 3,000 psi. Common pressure range being in that 10,000 psi type range, maybe 20,000 psi, and as higher pressures like 30, 40, 60, 75, or 100,000 psi. It's dangerous than gas at higher pressures, but it's important that we don't. It's always safe. It is possible to end up with a dangerous situation even with liquid as the media at high pressures. Always see guidelines and take proper care when working with pressure. It's contamination of the device under test. Specifically, if you're calibrating, say, a number of transmitters used throughout a facility, first transmitter using oil, that can cause damage, or that can cause issues depending upon what that transmitter is used to calibrate. And even then, once it's contaminated with oil, that may result in contamination of other devices as well. Especially an issue for dial gauges with large internal volumes. The gauges, especially a board-on-tube style dial gauge, can be difficult to clean out. All of the liquid media has been removed from the system, but being put back into service. This will have a much smaller internal cavity that's much easier to clean out, whereas dial gauges, especially larger dial gauges, will be to clean. Between medias, you have the choice often between oil or water. I choose one or the other. Well, oil is most common. One, be corrosive. Water obviously is essential to life, but it also can cause damage on different parts depending upon what materials they're made out of. So it provides a better lubricant. This is especially key when working with something like a dead tester, where lubrication between the piston and cylinder is very useful. Used in applications where oil is not acceptable, if it's hydrocarbon free. So if you decide between oil and water, to ask yourself is, will the process allow for that contamination? Will use oil cause a problem? If it won't, then use oil. And there's no different oils that you can use. Minerals are a silicon oil. If you can't use oil, then sometimes used. It can be used quite useful. Obviously, you need to take care to make sure that your item dried out after usage and aren't allowed to rust and so forth, and it isn't caused this way. To note that devices that are designed for use with water should be used with distilled water, not water. Sometimes people choose for a water-operated device because they go, okay, well, water is plenty available. I can get it at any sink, so to work with. But the real tap water obviously has a lot of different contaminants in it. This will break down the materials that our different reference standards or devices are made out of. So it's important that we use distilled water, not tap water. Okay, pick the media. We need to start looking at how we're going to do this calibration, the type of equipment we'll use, and how we're going to get our pressures. There are different types of pressure generation devices, and I'm showing a few of them here. For simple calibrations, especially of, say, dial gauges, it's very common to use things like a pressure pump or comparator. Here, as an example, is the P5514. This particular one is a hydraulic unit, but there's also pressure pumps that are pneumatic. That will generate pressure by turning the screw press. I have two connections, one for your reference gauge and one for your device under test, so you can easily compare the readings of the two. Examples are deadweight testers, like the P3124 that's shown here. This one is generating pressure in the same sort of way as far as the screw press, but then the pressure is stabilized and the measurement is done the floating piston with masses creating a force being applied to the top of the piston. We'll talk that a bit more later on. Here would be an example of a piston gauge, this being the PG7601. Works on the same principle as the P3124 as far as a floating piston with being applied to it. Another example is a gas unit and a much more precise instrument than we traditionally refer to as deadweight testers. The example is a pressure controller. Here, it has a built-in algorithm and functionality to maintain a stable pressure while at the set point. So operation is simple as you type in the pressure you're looking for, it controls that pressure and controls the system to keep stable pressure while you're there. These can provide with a stable pressure of stability using different techniques. Unstable. Why is it so difficult to get a stable pressure? Well, the gas law. More applications than just the division of footballs in a football game. It's very much key to understanding why we have an unstable pressure when doing a calibration. Gas constant is given as PV equals nRT. You can set for pressure and use an evaluation tool to look at why your pressure is being unstable. That pressure equals nRT divided by V. What are these different variables? P obviously is pressure. N molecules in the system is a constant, temperature, and V is volume. What is also, well, basically looking at that there's about 3 different things will affect pressure and thus cause it to be unstable. First, as the name of the system changes, the pressure changes with it. We, by design, will screw press when, for example, the screw pump used to change the pressure on a hydraulic pressure comparator. We're volume in the system, but when we make the volume smaller, we make the pressure greater. It is a way that creates instability. At pressure, the internal diameter of the tubing may swell, changes the volume in the system. There's instability at higher pressures. And the number of molecules is perhaps the most obvious way that you have instability in a system. We control the pressure in the system as far as we let air into the system to increase pressure. We vent the air out of the system to decrease pressure. This is a basic example of how a pressure controller works, a pneumatic pressure controller. But and changes, perhaps not by design, but we have a problem with our system. If we have a leak, that's simply the number of molecules in the system is decreasing and our pressure decreases with it. The temperature changes, or T changes, the temperature changes with it. Temperature goes up. When the pressure stabilizes, a hydraulic pressure comparator, screw press, the pressure goes up. That will cause the temperature of the media to go up as well. Without turning the screw press and allow it to stabilize, the temperature will then try to decrease, going back to ambient. As it goes down, the pressure goes down, and you have a leak. I'll find yourself chasing a leak that doesn't exist simply because it's not a leak, it's simply temperature effects. To analyze it. Well, we use different methods depending upon the type of instrument we're using. With a pump or comparator, they're adding molecules, like you'll see in a pneumatic pump, where you press on the lever arm, air is pushed into the system. As you pull up on the lever arm, is drawn in from the atmosphere and then pushed into the system as you press down again. Or the pressure changed by changing the volume of the system, like with a hydraulic pump. With a pump or comparator, it's more difficult to stabilize out the temperature effects, but then through manipulation of the variable volume or through patience. What do you mean by that? With the variable volume or the screw press, as before, you turn press, your pressure goes up. With a screw press, you're allowing your pressure to stabilize, but it'll go down because of the temperature effects. If you screw press the other direction, causing the volume to increase, you will go down, but the effects will now work in reverse, and the temperature will go up. Common technique is perhaps above the pressure that you're intending for, and turn the screw press in the opposite direction, let it go down to just below the set point, and creep back up to the pressure and stabilize at the pressure. But you need to be careful when doing this that you don't go too far past the point where you're causing your view hysteresis of the gauge. Hysteresis being the behavior of a gauge such that when you're displaying a different pressure, whether you're increasing to get to that pressure or decreasing to get to that pressure. But my overshoot around the set point normally does not impact your ability to view the hysteresis. That is the difference between a leak, the number of molecules leaving the system, or its effects, is the temperature effects eventually dissipate and go away. That is, you generate the pressure, you turn the screw press, the pressure will decrease as with the temperature effects, but the decrease will slow down, and eventually your pressure will stabilize. Take a few minutes, though, to get to. It stabilizes pressure in a very much different way. The required at that point, letting in or venting out air to over temperature effects. That's it. It will increase by changing the number of molecules in the system. While at the set point, it's continuously observing what the pressure is and minute changes as required to provide a stable pressure. When temperature effects are in play, there's inherently going to be some oscillation or some instability in the pressure, just because the pressure controller is looking at for the pressure to change, and then it's making a change to the number of molecules to offset that. So you see some movement around the pressure, but with a well-tuned pressure controller and a good system, that entity will be insignificant in your calibration. A works best in a free system. Control the number of molecules, not some outside leak control the number of molecules. Pressure controllers can need a leak. And the pressure controller is given off to the right. This is the 2271A. It was a new pressure controller calibrator provided by Fluke Calibration. The method for having a stable pressure, to stay as a pressure, is the floating piston as used in a deadweight tester or piston gauge. Properly built and properly cleaned piston can provide you with the most stable pressure possible. Defined as a force by the masses divided by area. And this is the area, the effective area of the free floating piston. Our diagram to the right, we have our force 1, which mass acting down, asserted by gravity, acting down on the piston. We have effective area given by A sub E, which is effective area of the piston cylinder, and there's a force being applied, pushing it up and causing the whole system to be the piston to be floating. That force being pushed up is the calibration media, the pressure of the system. The piston sinks. So while we talk about it floating, will be naturally sinking while pressure. The natural sinking of the piston causes the volume of the system and the molecules to change. That is, as the piston sinks, internal volume of the system decreases by the size of the piston, and media would escape the annulus, or the gap between the piston and the cylinder. This small operation of the instrument is expected that the piston should slowly sink as it's operating. That's usually a sign that you have a leak in your system somewhere. Pressure is decreasing. Means other than just the leak around the piston cylinder. The of the piston offsets the temperature effects. That's while the piston is floating. It's defined. The pressure is defined as force divided by area. As the force is the same and the area is the same, the pressure will be the same. As long as it's sinking, you have the same pressure. So the sinking effect offsets the temperature effects and creates a very stable pressure. The key to that stability is there only really be two forces at play: the force of the masses down on the piston, masses accelerated by gravity pushing down on the piston, and the force generated by the pressure pushing up on the piston. An additional force like friction between the piston and cylinder then have instability in your pressure measurement. But as long as it's properly built and clean, they have a very stable pressure when you deadweight tester or piston gauge. It's important to have stable pressure when doing calibration. Well, what the pressure is. If the pressure is unstable, that makes it more difficult. If the pressure is oscillating around a point, you perhaps can take averages, the pressure over a period of time, or there's other methods where you can get the instability to be insignificant in your system. But by having a stable pressure, it makes it easier to understand what the actual pressure in the system is, making it much easier to determine is your device under test in or out of tolerance. Very much a discussion on stability is the question of resolution. The EDWT, we refer to as the electronic deadweight tester, and can be used in any of the same applications as a deadweight tester, but as a more modern replacement. It's more similar to a pressure comparator in that it generates pressure through the use of a screw you're using a very accurate, very precise reference gauge, the built-in RPM4, to measure the pressure. Standards like this oftentimes show many digits, and that's necessary when working at the highest uncertainty levels. But using this to calibrate devices like pressure gauges, have too many digits, the pressure will never appear stable. It looks like it's always changing. Those last few digits are always changing. Why digits changing is because of the instability that we talked about before, sometimes temperature effects. Often, those extra digits of resolution aren't necessary for the calibration being performed. It's very useful to reduce the resolution so that a sufficient number of digits for the calibration are played, but not too many digits. And the rule of thumb is to have one more digit resolution than the center test that you're calibrating. Ensure that you have sufficient resolution to under the true behavior of the gauge, but at the time not confuse the operator with digits that are unnecessary and that cause the pressure to appear more to be stable, even within the realm of the application, it's sufficiently stable. Okay, so we've picked the media, we had to generate the pressure and making sure that we've got it displayed properly. Now contaminate our system here. These under tests are often dirty, depending on the application they're used in, what process they're used, the different dirts, oil, or other debris, and that debris can contaminate your reference standard or other DUTs. A gauge that is full of oil and you run your system, even if you have a gas system as your reference standard, connect the next device because the oil from the first device under test gets the system and then expose other devices to that oil as well. This causes major problems. There's ways to tackle this issue. One often done is to clean the devices under test beforehand, or you take steps to protect the reference standard in other ways. Cleaning this under test could be as simple as washing it with alcohol or similar, especially with a dial gauge with a large internal volume form of tube, be very difficult. You can use other devices to help with the issue of contamination, like filter traps or liquid traps. So shown here is a liquid trap. Basically, the device under test will be connected to the top with the reference device connected below, and internally it basically works as a mix where the media must flow down and back up in order to get from gauge or from the device under test to the reference gauge, and that's in direction from down to up situation where liquids that are trapped in the media fall out of suspension due to gravity and to end up in the ref gauge or the reference standard. Where you have separators. For example, here this is a liquid-to-liquid separator. So there's a diaphragm in the middle. So the two media never actually come in contact with each other. Instead, pressure from the standard on the bottom pushes up on the diaphragm, changing the pressure the top half of the system where the device under test is connected, resulting so you have a compression between the two of the media. They're useful in situations where you have, say, a hydraulic deadweight tester that works on oil, but you want to contaminate your device under test with oil. You want to keep it, say, with water. So use your oil deadweight tester on the bottom, fill that up with water, and so now your device under test is seeing water, and your reference or your deadweight tester is being operated in oil. Given on the deadweight tester with examining your device under test. There are additional uncertainties or sources of error associated with these, but useful in many applications, especially for higher pressures. Another example is setting up a system to have unidirectional flow. That is, the media flows from the reference standard to device under test when going up in pressure, and then when going down in pressure, instead of, as you normally would do, having the media flow from the device under test back to the standard or the reference, having it in a different direction outside the system. Of a device that does this is what's shown here is the Contamination Prevention system that's available for use with the 2271A or the 6270A, though it actually makes use of pretty much all of these different systems, where it has a built-in gravity trap, filter system, and unidirectional flow. So it'll up in pressure, it controls using the pressure controller going up. As you go down in pressure for the large changes in pressure, it uses internal valves in the CPS to vent the air out of the system here instead of having it go back through the pressure controller. Okay. Exercising. And why should I do it? This is especially important when calibrating traditional dial gauges. Actually, the process of taking the device under test to the maximum and minimum of its range multiple times. The normal most is 3 times. It is done at the beginning of the calibration process. So, sensing elements, especially used on dial gauges, will behave differently if they have recently been pressurized. That if you take them out of the box in the morning, them cold, you get a different value than way through the day after they've been seen pressure multiple times, and that elastic element has been worked. Whenever possible, be running the actual usage of the instrument. The instrument normally is that pressure has been applied to it multiple times. Therefore, we exercise the device under test in order to put it in the same state in which it is used. Is it necessary to exercise the device under test? Well, a lot of more modern technologies, some of the technologies for measuring pressure, are susceptible to this elastic element behavior. Always seen as good practice. A common thing is something, especially when calibrating dial gauges, should be considered. Of calibrating dial gauges is dealing with and maximizing the limit resolution that a dial gauge has. So even one with a very large diameter or large face, you basically the pressure because the pressure is up to the dial gauge. Is the shape of the elastic element, and that moves the pointer on the face, and the pointing to the different numbers on the face of the gauge. Limited by your ability to observe what pressure the pointer is pointing to. Easy sometimes, but it can also be very difficult. And an untrained eye, it can be difficult to get good repeatability in this. When it's stabilized, such that the reference standard is reading the cardinal pressure. Is, for example, if I'm calibrating this on a pressure comparator, the pressure, so that I'm reading 50 psi, and the pressure stabilized there at 50 psi. So I'm reading 50 psi on my reference device with a digital display. The pointer, the gauge needle, will most likely be pointing in between 2 demarcations. It may be pointing exactly at 50 psi. That is, I've selected a gauge to calibrate that has no error at that point. But as you know, the point of calibration is the fact that gauges and devices rarely have exactly no error. So much more common that we're going to get a point where the needle is slightly off of a cardinal point. It's halfway between 50 and 51, or 50 and 50.5. Interpolate what value it's on. There's different techniques to do so, and when properly followed, can give you good repeatability, but you have limitations on your overall resolution. This approach is to jog the pressure or make minor modifications to the pressure so that it is on the cardinal point. The standard will have more resolution. It will be easier to read. And the reference standard will be off of the cardinal point. So, for example, control the pressure up to be approximately 50 psi. I'm going to jog that pressure, make my changes to it until my dial gauge is reading 50 psi exactly. The reference gauge may now be reading 49.83. This is in my overall experiment and a better understanding of the behavior of the dial gauge. Who practice do not follow this procedure. It's an example of, well, work it and what the dial gauge is reading immediately after the pressure is changed versus allowing it to stabilize at the pressure. That's dependent upon the application. Application of most dial gauges, this is an acceptable and common practice. A bit, and we'll switch from some tips that are specific for dial gauges to talking about the calibration of pressure transmitters. Transmitter, as connected to our 2271A, would be a device that will measure pressure that's been applied to it and output some sort of electrical signal. Off of it outputs a milliamp, say a 4 to 20 milliamp signal. It'll be the transmitter. You can see here the term transducer. Oftentimes refers to a device where it pressure and outputs a voltage. Okay. With such a device, we need to do a number of steps. We need to be able to apply the pressure, make sure it's measure that pressure, provide voltage to the device under test, that is, turn it on, and the output of the device under test. Measure the output of the device under test need to be considered when calculating the test uncertainty ratio. You'll see situations where, since you're calibrating a pressure device, you may look at, okay, is my pressure standard sufficiently accurate for this measurement? And comparing the specifications of your device under test with the measurement specifications of your. This is full, but it's only the first step. We need to look at measure the output of the device under test. Not sufficient. If we're using a multimeter that does not have sufficient accuracy or capability, we can get incorrect results in our calibration. Consider our ability to measure the output of the device under test when looking at the capability of our system. The device under test output is a ratio of the supply voltage. If its output is X number of millivolts per voltage of supply pressure or supply voltage provided, to measure the supply voltage as well, and get that measurement, that capability in our as well. Device 71A or handheld devices like the Fluke 718 that provide both pressure measurement and also measurement can be very useful in calibrating pressure transmitters, as you have the ability in one device to measure both what's being supplied to the transmitter as well as what's being outputted from the transmitter. Talk about data collection and the automation of data collection. can be accomplished whether calibrating gauges or transmitters. Obviously, with something like a dial gauge, it becomes a bit more difficult as you need to physically read the dial gauge. Whereas transmitter, if you're using a device that has a digital output to output of the transmitter, then you could perhaps fully automate the process. Dial gauge, you have to have some level of user intervention to read the dial gauge. There have been scenarios where people have used digital cameras or so forth to take a picture of the dial gauge face, but can be very challenging because as the pressure changes on a large dial gauge face, you're not necessarily looking at the center of the dial gauge. Or focusing on the center of the dial gauge, you're focusing on looking straight at where the needle is. So when taking the picture with camera, you have to kind of move the camera with it. It's still preferable to have a user involved in that sort of calibration, but you still have some level of automation. Automate the generation of the pressure, and you can automate the recording of data. By doing so, you can ensure that the same process is followed every time. For calibration, we want reusability of process. You can eliminate transcription errors. Anytime that you have an operator write down a number on a piece of paper, no matter how good the operator is, no matter how many cups of coffee he's had that morning, he has the potential of writing a number down wrong or writing down two numbers transposed. You can remove that potential for error. It's a very good thing. You can reduce the touch time, improving efficiency. Especially in the example of the automated system for the calibration of, say, a transmitter, where the technician can set it up at the beginning, hit go, and away, reducing the touch time. Perhaps the technician can be then operating a different device, or he can be drinking that cup of coffee. Okay, so we made the data collection. We can do it through software like Compass for Pressure that operates on a PC, or we can do it using built-in capability of some of our different calibrators, where you can set up and run a specified calibration procedure and have it store the data points at each one, creating a text file that we can then turn into our calibration report. Either type of method can be sufficient depending on the calibration being performed. Okay. 7 tips. We need the right media, oil, water. We're going to stabilize the pressure and ensure that we have a good stable pressure. Pre-examination of both our reference standard and other devices under test. We exercise our device under test as our reference standard. Maximize the limited resolution of a dial gauge. The electrical measurement, and the benefits are automating the data collection during our calibration. Okay. We'll open it up for questions. So if you have any questions, please send them through the Q&A or chat windows. The questions here, so give me 1 minute. So again, questions, go ahead and send them through the Q&A or chat windows. Use glycerin for a no oil calibration of a gauge. Also, can you mix the glycerin with water or alcohol to make the mix more fluid? Depending upon the application, it is possible to use glycerin, alcohol. Alcohol, you need to be careful with devices that have, say, a plastic reservoir, as some plastics react with alcohol. The alcohol will cause them to crack. It is very common to mix water and alcohol together as a calibration media. And the example of the deadweight tester / piston gauge is the system not closed when testing. If so, how does the number of molecules change when piston sinks? Back to my diagram of the tester and piston gauge. System be considered closed in all aspects except for there's a very small gap or annulus between the piston and the cylinder. So here, the piston is the part in green, the cylinder is the piece in blue. You can think of a cross section. As the piston is floating, fluid will traverse between the piston and the cylinder. So it will escape between the piston and the cylinder. This is somewhat different from we normally think of in a system because while the media is leaking out of the system between there, if the annulus is too large as a liquid system, you could actually have a puddle of oil forming at the base of your normally the is going out of the system in one place. In order to maintain our pressure, we're pushing more media in somewhere else, and we're creating a flow through the system. With a floating piston, you do not have that flow because the leak the media leaving the system, the molecules leaving the system, are overcome by the volume of the system changing. That is, the piston sinking. So the area the volume that was filled up with those molecules leaving the system is now filled up with the piston. So you don't have a flow through the system. You just have molecules leaking between the piston and the cylinder. Okay. Users do not perform detailed testing on their digital gauges. Is hysteresis less of a factor with digital pressure gauges? Always. Hysteresis, once again, is defined as the difference in behavior caused by the pressure reaching the pressure either going up or versus going down. If you take pressure points ascending, say 0, 25, 50, 75, 100, and same pressure points go down, setting 50, 25 back to 0. With hysteresis, you see it most predominantly towards the middle. So at 50, maybe you're reading 50.1 going up and 49.9 going down. That hysteresis of 0.2. Now the question is, okay, well, you see meters or other calibration people performing that test of going both up and down on opposite devices, especially on digital gauges. Gauges, the elastic element or the sensing element will be silicon. This is likely to exhibit hysteresis depending upon how it's packaged, as a metallic board-on tube is more likely to show hysteresis. In the world, we would collect as much data as possible, and so we would perform our calibrations as an infinite number of points in both directions. But if the device is shown to not have hysteresis, then it can oftentimes be determined that it's not necessary to continue taking those points. The pressure goes slightly above the pressure you want to calibrate on and then return it to the pressure. Do you mean turning the screw or just waiting for the temperature drop and consequently the pressure? Both. One up is, yes, you go turn the screw press, you go slightly above the pressure that you want to go to. Temperature effects dissipate, the pressure will go slightly down, and you'll end up very close to the pressure that you need to attain. It's noted, especially on calibrating pressure transmitters, hitting exact cardinal pressure is not really necessary as long as you record the actual pressure that you're taking your measurement at. The suggestion that was also provided is that you go above the pressure to decrease, quickly move your screw press just slightly so it goes, so you may adjust the pressure to below the point you want to go to, and temperature effects will cause it to slightly increase in pressure and lies out at the pressure point. Okay. Any questions? And thank you for your questions. Once the presentation and with the link recording will be sent out later this week. Once again, thank you. We appreciate your time, and happy calibrating. Have a day.